Okay, getting back into it again. These are the places on the internet that I downloaded these practice exams from. Hopefully they're still there, who knows. And we left off on number 11 here. So the piecewise linear graphs of the functions f and g are shown in the figure above. If the function we're naming h is equal to f of g of x, what is the value of the derivative of h at the value of 3? So this is a little tricky kind of composite function, if you will, where we're saying we're going to take the x value, run it through the g function, and then whatever the value of that is essentially the y value on the g. Then we take that and cycle it as the new x into the f function. So it's a composite function. It's one function taking its output as the input of another function. And there's the trick here is that they don't tell you what the functions are really as an equation, but they give it to you in the pictorial form. So when we have a composite function and we need to take the derivative, that is called the chain rule. So the derivative of that function of the f of g equals the derivative of f composite with g multiplied by the derivative of g. So for here, we want to know what all this is when x equals 3. So we'll write that the derivative of f for g of 3 times the derivative of g at 3. And so first of all, we will question what is g of 3. So on the graph here, here's 1, here's 2, here's 3. And here's the line g, so we'll try to figure out what is that point here. So this is where you can observe that it's at point 20 there, and 3, 4, 5, 1, 2, 3, 4. So that's at point 5, 4 up there. And so this distance is 3, this distance is 4, and to get to we're interested in x equals 3 right there. So per the slope, we have it goes up by 4 and over by 3, so that the slope is 4/3. Change in y over change over x. Change in y over change in x is 4/3, and we've gone 1x over, so this point is going to be 4/3 up from here at the 20. So that point we know is 3 4/3. That point there. So we can rewrite that as the derivative of f at x equals 4/3, because that's the y value that we got out of g at x equals 3. And then the derivative of g at that point where we already found that, it's the slope 4/3. That's the derivative. So it's just 4/3. So then what is the derivative or the slope of f at x equals 4/3? Well, it turns out that the slope of f is consistent over the entire thing. 4/3 is about there, but kind of didn't even really need to care about that so much because it's the same over the whole thing. And we can count 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and we can tell that it's just a slope of -1. So that turns this into -1 times 4/3, and that equals -4/3. So the answer here is going to be B. Okay, so the next one, number 12. This is a limit problem, and the limit problems you're kind of wide and varied. You gotta approach them differently depending on what is being thrown at you. So basically, you have the cosine of a half plus the h minus the cosine of a half. So what you're telling here is it's almost the same thing being subtracted from itself, except you get a little bit of the variance of the h there, and then you're dividing by the h, and we're asking what is the limit as h approaches 0. So at h of 0, of course, this goes away, and you're just subtracting the same thing from itself, and that would be 0. But then you would also be dividing by 0, and you can't do that, and that usually causes something funny to happen in the graph. And if this were a point where you could just punch it into a calculator and see the graph, that would be really easy. But this is not in the section where you're allowed to do that. So we kind of have to approach it more mathematically to figure out what we're doing. So we're gonna remember our unit circle here, and 0, pi, half pi. So we're interested in the cosine at half pi, which is going to be this point here. And of course, the cosine of an angle equals the x value. So the x value up here is 0. So the cosine of half pi is usually 0. But it's asking us plus h as h is approaching 0. So we have to also consider as h approaches 0 from the positive direction, and h approaches 0 from the negative direction, because this doesn't have a sign there, so it's asking from both sides, both directions. So we have to consider an h that is a very small number but a positive number, and an h that is a very small number but a negative number. So what we get from that is an angle that is just a little bit that way, and an angle that's just a little bit that way. And so we track down to the x value, and if you are subtracting, if h is a negative number and your angle is going to be just a little bit smaller, then you're going to have just a very small little x value there, and the cosine is going to be a small positive number. But if h is a positive number and you're adding to the angle and going more this way, it's going to be going just a little bit into the negative x values. And here's the point where we figure that, well, we're talking about as h approaches 0. So let's imagine that it's just a very, 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 very small number, essentially an infinitesimal number. And so we just kind of round, and we notice that for again, for a negative h, you get a positive number here, which would be a positive number on top, and the negative number on the very, very small positive number on top, and a very small negative number on the bottom. Whereas if h is I think I got myself lost whether I said that the right way or not. If h is a negative number, then we get a very small positive number as a result of this. Very small positive number over a very small negative number. But if h is a positive number, then we're going over here just a little bit. So everything on top is a very small negative number over a very small positive number. And what we can conclude from that is a very small number over another very small number is going to be pretty close to 1. We can say it's 1. And that negative sign is either going to be on the top or on the bottom. You're always going to have a negative sign. So it's going to be -1 one way or another. And if you care to pull out your calculator and then graph that, you can see that it kind of heads at -1 from both directions. It's not quite reaching -1, but getting very close to that if you zoom in closer and closer on very small values for the h. Okay, then. Moving on from there, we will go to problem 13 here. Actually, we're not. Problem 13, this involves something called implicit differentiation, and that's just because the x's and the y's are all mixed together in a kind of nasty way. This is one of those topics in calculus that is taught very briefly. If you look at the textbooks, there's like one section on it, and then you do it and you kind of move on, and you don't ever use it again, and then nothing is built upon it. So it's just a very brief kind of thing. In this practice exam, implicit differentiation only shows up in one problem. So I suspect on other tests, from other years, similarly at most is one problem. Just learning how to do this and taking the time to do this on test day because it's extra complicated is just not worth it, I think. If as long as you're good at all the other things that is involved on the test, one problem isn't going to sink you. If one problem is going to sink you, then you're not not doing well enough on the test to be doing it anyway. So just as per the answer key, this one is C, but we're not going to worry about why that is because it's just tricky and not really worth our time on that on test day. Just be skipping that right over. Okay, so Number 14 then. So this is a notation, dy over dx, and with the 3's, so we're asking the third derivative. This is the first derivative, dy over dx. And then this is the third derivative. If it was d squared y or dx squared, that's the second derivative. But we're skipping the second derivative. This is the third derivative. So we're asking where is, for which of the following functions does the first derivative equal the third derivative? So let's look at these one at a time. For Roman numeral 1, we have e to the power of x, and we know that e to the power of the derivative of e to the power of the x is itself. So you can take the first derivative, the second derivative, the third derivative, as many derivatives as you want, and it is always going to equal itself. So we say for that, yes, it is. So on e to the negative x, that's a little bit different because you have that negative x here. And just to show what happens, we're going to apply the chain rule. And so again, the chain rule says the derivative of f of g of x times the derivative of g. And in this case, the f is e to the x, and the g is the negative x. So the derivative of that is itself, but the derivative of negative x we know is -1, because that's x to the first. Subtract that goes away, bring the 1 down, and then you just keep the negative. So we fill that in there. E, the regular original feeds back in. E to the negative x times this one, fill that into there, -1. So the first derivative of that is -e to the negative x. That's the first derivative. Now if we do the second derivative, we run through all that again, and we get another negative popping out again. So this is the first derivative. If we do the second derivative, another negative comes out, and we return to the original. And then, of course, the third derivative, the negative comes out again, and it's back. So in this one, it's not the same every time, but it's alternating. First the negative, then the negative goes away, then the negative comes back. We went to the fourth derivative, the negative will go away again. And because the question is asking, when is the first derivative equal to the third derivative? Well, those are both -e to the negative x, as it flips back and forth. So because we're skipping over the second, they actually are equal to each other. So for that one, yes, it is. So Roman numeral number 3, we're asking the derivative of the sine. And again, just the trig, these are ones that you just have to know, just have to memorize, like e to the x equals itself. You have to know that the derivative of sine equals the cosine, and you have to know that the derivative of the cosine is negative sine. So those just memorize them. You just have to memorize those. So we can kind of follow that through. If this is the original, this is the first derivative of the sine, and then we go down there, and so now the second derivative is the negative sine of x. So you can imagine what is the derivative of negative sign going to be? Well, that the negative follows through, and you're going to have negative cosine. First derivative, second derivative, third derivative, and negative cosine, and that takes you back to sine, because you're negativing, and the negative plus well, two negatives makes the positive. Let's just say that. So again, we have a cycle here, but instead of alternating every other one, we have a cycle of 4. It takes us 4 derivatives to get back to the original. So the first derivative is the the first derivative is the cosine, and the third derivative is the negative cosine. So they do not match. If you kept following through, the fourth, instead of every other derivative, it's every fourth derivative matches. But just the first derivative and the third derivative, they differ in signs. So for this one, it is not. So 1 and 2 are true, 3 is not true. So the answer is D. And then we're going to go to number 15 here. And here's another limit problem. And is asking, what is the limit as x approaches 0? And there's a minus sign. So that means as x approaches 0 from the negative direction, from the left. And then the function is 2x over the absolute value of x. So we need to visualize this graph, y equals 2x over the absolute value of x. Well, what's happening here, and obviously we have an x on the top and an x on the bottom, so those are going to pretty much cancel out, and we're going to basically have y equals 2, except that because you have the absolute value, what you're doing is flipping the signs. When x is positive, it just cancels out normally, but when x is negative, you have that negative up here, but the negative goes away down there. If x is negative 3, then you have 2 times negative 3 over positive 3. So you cancel those out, and you're still left with the negative 2. So you can envision the graph 1, 2, well, negative 1, negative 2. You can envision the graph like this, that on the positive side, y equals 2, and on the negative side, y equals negative 2, y equals 2, y equals negative 2. Down there, it's just a horizontal line, because the x's cancel out, and all that's doing is flipping the sign. So if the question asked the limit as x approaches 0 from both sides, you would have to say it doesn't exist, because when you're coming from this direction, it's positive 2, and when you're coming from this direction, it's negative 2. So that does not exist. But it actually asks us, what is the limit as x approaches 0 from the negative direction from the left? So that's here. And even though there is no, the graph doesn't exist at x equals 0, because you have the divide by 0 error, but right before you get to x equals 0, everything is at -2. So the actual answer is A, -2.